Hello everyone. Today we'll be talking about wave behavior. So the first chapter of wave behavior is simple harmonic motion. Now you're gonna encounter something that's gonna be quite overwhelming. It's these list of formulas. So let's start tackling them down one by one. So we'll talk about the formulas and then talk about the images. So the first formula you have is acceleration in simple harmonic motion. So the A stands for acceleration, the W or omega stands for angular velocity or angular frequency, depending on how you want to call it, and then X represents the distance. Then you have T, which is known as the period, which is 1 over the frequency. Uh, Period also means like how long it takes for one wave to oscillate full. So like how long does it take for that thing to do a whole 360 degrees? And it's usually measured in seconds. The second part we have is the angular velocity or frequency. Uh, and the way we calculate it is 2 pi over t. So in this case, we're calculating in radians. Otherwise, it would be like 360 degrees or one whole circle over the amount of time it took for that circle, which makes sense because if you know the velocity formulas from like linear stuff, then you understand like velocity is equal to distance over time. That's where it comes from. Then we have another formula, which is how to calculate the period when it comes to the spring constant. So in this case, the spring constant is k, and you have mass over the spring constant, the square root of that times 2 pi, which is one whole circle. Uh, yeah. And then the next one you have is another one to calculate for springs, which is 2 pi times root of 1 over gravity. Uh, the other formulas are HL, so I'll go over that after we go over the images. So if we look at the images, you will see that we have, let's look at the bottom one first. So first of all is the sort of, it's a spring, and the graph right now is the amplitude time graph. So as time continues, the amplitude goes from you know zero, like minus amplitude to plus amplitude, and then it reaches zero at a certain point. It was there for a few seconds. That is known as the equilibrium point. Then the point where the amplitude is the greatest, or like the plus, is known as I think it's the like trough, and the point that's the lowest amplitude is known as the crest. Uh, right. Now we're gonna go over the big sort of moving circle. Uh, this is basically representing the x and y coordinates of an object in simple harmonic motion, where you have sort of the big, you have, want to call it a ball, but it's a particle in reality, rotating around, and then you have the radius, which will serve as like the distance between the 2 points. So the radius is always constant because the x values and y values are always constant. This is something we learned like last year in trigonometry. Uh, well, I think yeah. So it's the sine and cosine. That's where we're also gonna go to the HL. Alongside this, you also have another graph, which is a wavelength and sort of or like a distance time graph. And here you're able to calculate. Let's see, as it goes from equilibrium point uh, one to the next set of equilibrium. So it has to go over one trough and one crest to be considered one full wavelength. So if you're doing your exams and you see this, you know that this is one full wavelength. Then you also have the calculation of the velocity of the wavelength, which is like velocity is equal to, I mean, velocity of the wave, which is equal to lambda, which is the wavelength, times the frequency, which can be converted into distance over time. And as I stated before, 2 pi is equal to 360 degrees. Now we're going to go over the more intimidating HL formulas. Uh, So in this case, x is the position, x0 is the amplitude of the motion, uh, omega is the frequency, angular frequency, plus this weird letter, which is the phase. It's like phi, I think. And then so we know that x, which is the position we're trying to find, is equal to this formula. Then we have velocity, where velocity is equal to angular frequency times x0 plus uh, angular frequency times time plus the phase. Then we have sort of the total energy in the system, which is one half of mass times uh, angular frequency squared times amplitude squared. For this and the next formula, you can look at the graph to the bottom right, where you have another spring, which is sort of perpetuating the graph over there. And beneath it, you can see of the potential energies. So you have kinetic energy at one point, and then you have potential energy. At minus amplitude, you have the greatest potential energy, and at plus amplitude, you have the greatest potential energy. And then kinetic energy is greatest at the equilibrium point where it's zero. So if we just look at it logically, as you can see, when the spring is extended to the maximum, there's more potential energy for it to return to the equilibrium point, and when it's at the equilibrium point, there's more kinetic energy. There's the most kinetic energy as it is in motion at the most at that time. We'll look at further graphs, which I will help to explain. Last equation on this slide would be the the potential energy, which is this formula. It's the same for the potential. No, it's the same for kinetic energy, which is one half of mass times angular frequency squared times the position squared. Yes. So next slide. Right. Uh, so here we have a lot of graphs. This will be like pivotal to the test because, as you know, we had in the multiple choice, we had a lot of these. So this is a displacement time graph for a wave. It was also there in the previous slide, and yes, you could see that from one point to like the whole graph basically for the first one shows you the wavelength. Uh, then this is also like a cool little diagram to show you that the velocity and displacement changes. So as when the displacement is maximum, your velocity is zero, and then when displacement is minimum, then your velocity is maximum. This also sort of shows the kinetic energy and potential energy formula. So in this case, like it's not accurate to say this, but to create a better conceptual understanding, potential energy is maximum when the displacement is maximum, and the kinetic energy is maximum when the velocity. Right. So then we have more graphs to sort of explain. So this is the velocity time graph for the displacement time graph. So they're the same wave, and this is sort of uh, in the continuance of that. The velocity sort of moves with this, and since velocity is a vector component, it does have direction as well. And that's why you have sort of the negative quadrants included in the velocity displacement graph. Then you also have the acceleration displacement graph, which shows us the acceleration. So obviously when velocity is like maximum, then the acceleration is minimum, and then it's goes around because it's a simple harmonic motion, so it all goes in a circle. And then again, you have the potential and kinetic energies here, which you can also see nicely aligned with the displacement of that. So, next one. I'm going to talk about the wave models. So, the two key components of the wave models. These are the waves that can like sort of transfer information. The longitudinal waves and the transverse waves. So we're gonna quickly talk about these. Give you a quick definition. Longitudinal waves, they're the waves that move in the same direction as the medium they are traveling through. So an example of this is like a slinky, which is like big, like thing, metal thing usually, and it has things going through. Or you can also think of air. As I'm talking to you right now, uh, there's like a speaker that's emitting the sound waves, and then particles of the air are hitting each other, and they're moving as this diagram shows, uh, which is a longitudinal wave. Then you have transverse waves, uh, where the particle moves more up and down in the position it is, sort of. And for example, light waves, where they don't really like move to you, but they just sort of go up and down, and then we perceive that as information. There's also waves on water, where the particles are moving up and down, and the wave itself is like going through it. And even a guitar string. So when you like pluck it, it vibrates. The string, like the contents of the string, don't move, but the wave is sending information from one point to the end of the guitar, where the sound is then reverberated. Right. Um, then this sort of graph, it shows a lot of things. It shows the distance as the wave travels. It shows the amplitude. It shows maximum rarefaction, maximum compression. So these were like the troughs and crests I was referring to before. Uh, it is an example of, I think, a longitudinal wave. So it's a longitudinal wave graph, and you can calculate the wavelength by measuring the distance from the peaks or the lows. The frequency for this would be the amount of cycles per second. So you don't have the time here, but then you would be able to calculate that from measuring two different points. Yes. Now we have an example of a longitudinal wave. So like I said, the particle sort of stays in place and it just moves up and right, yeah, a transversal wave, sorry. So yeah, here we have an example of a transverse wave, where the particle is moving up and down. Uh, and now these are different distance, so there's a distance graph and displacement time graph. If you have a displacement distance graph, then you can calculate the wavelength. If you have a displacement time graph, you can calculate the time period. Uh, it's just sort of logical. Yeah. Next, we have an illustration of what happens. So there was the sort of formula for the like V is equal to uh, something something. Uh, but yes, so basically, as the wavelength changes, the frequency. Yeah, so V is equal to sorry, V is equal to frequency times the wavelength. And so if the velocities of the waves are the same, then the frequencies will change. Now, what this means is that, and the wavelength will also change. So here we have, in the first scenario, we have a long wavelength, but the frequency, which is like the amount of waves there are less compared to the one on the right, where the wavelengths are smaller, but the amount of them are high. You see more like peaks in the second one than you do in the first one. But they're traveling still at the same speed. You can see that by the sort of graph above of like longitudinal waves. You see that the particles aren't really moving faster in one scenario or another. Yes. This one is a very fun one. It is a electromagnetic wave. So your light waves, radio waves, X-rays, all of those. You have electric field E and you have a magnetic field B, and so it has a direction of propagation. So the direction the wave is moving in, which is X. And then this is like these components of it. So light, as we know, is more complex than we think it was. And so now you also have like two different sort of two, or at least one more dimension to factor in. But again, the idea is the same. You have the, if you want to calculate the wavelength, you do the troughs and the crests. And if you want to calculate anything else, just like a more complicated illustration. Yes. Then we have the Young's two slit variation. So, and we also have like a diffraction. I'll get into the Young slit in a bit later. But yes, so we have wave fronts, which are sort of the waves emitted from the source. So in this case, in the first case, it's a spherical wave, and then they're moving as so, and then they have direction as well. They're moving outward of the source. Then we have a plane wave. So like the first one, it could be from a droplet of water on a pond or a lake. And then you'd get these ripples very nicely that would look like this simplified. Then you have plane waves. So if you have sort of like really loud, like an array of speakers all emitting the same thing at the same frequency, then they will go in a straight line and continue through, and they don't diffract as much as the water and the waves would. Water and the waves and the water would. Then you also have sort of diffraction as a concept. So as you can see in the first two pictures, uh, you have a wave sort of trying to go through, and it has a wavelength. Then you have a slit or a gap, and then as the wave is getting pushed through, there are certain areas around it that get bent essentially, and then it starts moving curved because the wave is trying to send all of its information through. So the wavelength is if the wavelength is smaller than the gap, then there's less spreading, and then there's less diffraction. Uh, yeah. If the wavelength is similar to the size of the gap, then there's more spreading, and then there's more diffraction. So diffraction would be like the amount of angle essentially it starts spreading to. So like here you can see there's less angles. So this would be like maybe like 90 degrees from one point, and then the other one would be 180 degrees. After that, we also have uh, refraction, which is where an incident ray goes through, bounces on a surface, and then gets reflected across. You have theta 1 is always equal to theta 2 across the normal, which means if you ever have shown a light on glass, then there's light that hits the glass and then it bounces off. And then if you were to put or mark it down, then you'd be able to see the angle from one point is the same as the angle from the other. Then you also have refraction. So this happens when uh, a wave is traveling from one medium into a denser medium. So in this case, it would be, I would say, light traveling through glass from air. So first you have the laser, which points through, and then it hits the glass at the normal line, and then it gets refracted a bit. This happens because glass is more dense than air, and then there's more difference across it. Uh, as you can see, as it goes from air to glass, so a lesser dense medium to a more dense medium, uh, it goes closer to the refracted ray, closer to the normal, sorry. The refracted ray goes closer to the normal, and if it were to be the other way around, then it would go away from. Uh, so to calculate the refracted ray, you have Snell's law, which states that refractive index, which is this n essentially, so n1 over n2 is equal to sine theta 2 over sine theta 1, so the angles, uh, which is equal to the velocity of the wave in scenario 2 over the velocity of the wave scenario 1. So since the medium is more dense, if it were like a sound wave, then it would travel faster in the denser medium. Um, So like the speed of sound in air was like I think 343 meters per second, but the speed of sound in water is three times that. Uh, so that's because of the refracted indexes. So the velocity changes. Then you have something very interesting happening. So as I mentioned before, from a less dense medium, from a more dense medium to a less dense medium, it will go away from the normal. Now, if you tilt it enough at a certain point called the critical angle, the ray will completely refract. It will go so far away from the normal, precisely 90 degrees, for it to not be shown to the other side. So this is known as the critical angle, and then if you sort of shine the light from a further away angle, then you have something called total internal reflection, where the light sort of doesn't go outside to the air, but instead it continues in the glass. I messed up. This is superposition, though. My bad. But yes, so superposition. Uh, these waves are superposition, which means that, as you can see, when the troughs align, then the troughs form, the value becomes bigger. Then when they don't align, it reaches a point of zero. So when they're perfectly out of sync or out of phase, uh, then they're zero. And when they're perfectly in sync or in phase, then these two waves form a bigger wave, right? So the amplitude of that wave is increased. Uh, so yes, going back to path. So here you have two sources, two different waves, and now, as I stated before, you have the amplitudes aligning it sometimes and not aligning it sometimes. So when they are perfectly aligned, you have path difference of constructive interference. So in this case, as you can see, the wavelength of source 2 and the wavelength of source 1 are the same. The distance to point C is 4 wavelengths from source 1. Distance from point C from source 2 is 6 wavelengths. So to calculate this, we would say 6 wavelengths minus 4 wavelengths, and we see that's 2 wavelengths. And now, since we know that the path difference for constructive interference has to be the wavelength, it has to be the same amounts of wavelength, an integer form. It cannot be like a fraction, like 1/2, 1/3, or something. Uh, since it's 2 wavelengths, then we know that it is a path of constructive interference. You can also see by the images, if you were to count the circles, the bigger, like the darker ones, you would see that they both align and meet perfectly at that point. So at that point, you have superposition happening where the amplitude of those waves would be bigger. Then you also have destructive interference. Now, this is when, like you said, they're perfectly out of sync, uh, where the wavelength from one source meets only halfway through the other source. So if you were to pick a different point uh, and then calculate that, then you'd be able to see that one would cancel out the other. So one would be on a like a lower amplitude or negative amplitude, and the other would be positive. Then positive A minus A is equal to zero, so it would be an equilibrium point where nothing would happen, which is known as destructive interference. Now we have the Young two slit uh, uh, two slit experiment, Young's two slit experiment, um, where you have two sources that are shown through, or not even necessarily two, but you have two slits, uh, and then light is shown through the slits. Uh, so there you have constructive interference and destructive interference. As you can see, the awareness where there's constructive interference, there's like a clear, sort of thicker, bold line. And when there's destructive interference, there's white space. Then there's the formula for this, where you can calculate the separation of fringes uh, is equal to, or in this case, y is equal to lambda, which is the wavelength of the sources, times d, which is the distance between the sources, or distance between the slits, over over small. Oh, I meant to say uh that s, which is the difference between the slits, or in this case in the diagram it's y, is equal to the wavelength times the distance, which in this case would be l, over d, which is the distance between the slits. So s is equal to lambda d over d. It's a little bit hard to understand, but yes, it makes more sense when you look at it this way. So yes, as I said, you have a laser beam, and then you have two slits, and then as you have paths of constructive interference and destructive interference, and Then you have a better diagram to illustrate the points of constructive interference, points of destructive interference. And then the center point is called the central maximum. Then M1 is sort of the next path of destructive interference, and then so on and so forth. Yes, so the waves interfere in the regions where they overlap, and the bright fringes occur when the uh, lines intersect in the viewing screen. So where there's destructive interference. And yes, moving on. So this shows us how the change of each sort of variable affects uh, the S, which is the separation of the fringes or slit like fringes. So here it's the changing of the wavelength of the light source. So as the wavelength, I believe, decreases, then you have fewer slits, fewer fringes, which are the lines on the wall. And as the wavelength increases, you have lesser of them. Then you have the distance to the screen. So as the distance to the screen increases, you have lesser fringes. As the distance to the screen decreases, you have more fringes. Then you have the distance between the slits. As there's more distance between the slits, you get more fringes. As you have less distance between the slits, you get less fringes. This is all understood from the formula. So if you look at the formula, you'll see that as D increases, then then S increases. As lambda increases, S increases. As small d increases, lambda decreases. Uh, Now we have something very, very fun, which is determining the path difference with information of uh, this angle and the B, which is the distance between slits. So we take the midpoint of the slit, and then which is B over 2. Then if you do know your triangles right, you'll know that this theta of the first theta is equal to the second theta, they're the same. And we're able to calculate that the path difference between the top and the bottom is going to be B over 2 times sine theta. So we know the wave from the top of the slit has to travel a shorter distance, and the wave from the bottom of the slit has to travel a longer distance. So then we know that x over b over 2, x is equal to b over 2 sine theta. Um, then we have the intensities of it. So as you can see, single slit interference with finite width, then you have very fixed sort of intensity, it follows the curve properly. Then you have double slit with finite width slit. So here you see that there's different like areas of intensity and there's a variation between them. That's because of the constructive and destructive paths. So when it's highest, there's constructive interference. When it's lowest, it's destructive. Right. Now we're done with the most difficult part. It's not. Standing waves! Yay! So, standing waves are arguably the most annoying topic ever. But yes, in this situation, you have a graph representing the standing wave. So the blue is the standing wave as we would see it. You have antinodes and nodes. So antinodes are where it's moving the most, and nodes are where it's stationary at the equilibrium point. Then you have two waves, the green wave and the red wave. These are essentially the components of the blue wave broken down to make your lives harder. And then you can see sort of when they align perfectly, then there's constructive, and when they don't align, then there's destructive. It's just a visualization technique to help you understand better. Because when we start talking about standing waves, then things start changing. Right. So, now the most difficult part of it all. You have a standing wave. So this is a fixed standing wave. There's two nodes, one on each side, as you can see, goes throughout all of them. Uh, then you have the center. There's a formula to calculate this. Um, but yes. So essentially, you have a standing wave. I'll go back. Uh, where there's wavelength, the sort of the amount of I think harmonics they're called. So the first one is the first harmonic, second harmonic, third harmonic, fourth harmonic. So now let's look at it. So you have wavelength of the number of harmonic is equal to 2 times of the length over the. So in this case, the wavelength would be 2 times the length of this. In the second case, the wavelength is going to be equal to the length of this. And then in the third case, it's going to be 2L over 3, and 2L over 4, and so on and so forth. And then as you can see, there's antinodes and nodes to all the points. The best way to sort of calculate the wavelength is to like look at the fragmentation of it. So, for it to be one wavelength, it has to go up and down. So in the first one, it goes up one, and then it goes down. And so then that's one, that's two, oh, that's, sorry, that's 2 times the length. Here it goes up once and it goes down once in the same sort of uh, point A to point B. So it's one length, and then here it goes up once, down once, up once. So it's 2 times the length over 3. There's the formula for this, which is 2L over N. Next. Uh, Now you have standing waves, but you only have uh, one area with a fixed and then one area which is free. Also, you have one area where it's both are open-ended. For the both open-ended, the formulas are the same. They don't really change, and the concept is the same, so you can apply it similarly. However, when you have it in a closed open situation, then you have a different formula. Uh, Here it's gonna be um, the wavelength is equal to 4 times the length. So here you actually have like one. uh, So you have like 1.5 wavelengths. Um, I mean 1.5 sort of sections. Uh, so it's gonna be 4 times the length of the first section. So which is from one antinode to the second antinode. Over 2 times n, which is the amount of ups and downs there are. So in this case, it would just like one. Or like yeah, so 2 times that minus one. So in this case, it would be 4 times the length. And then it changes on and so forth. Yep, that's right. Now you have graphic visualization of like longitudinal wave and then pressure. So you have different particles, as you can see as the red dot, black particles, which show the majority. So the red particles show what's happening. So as you can see, there's nodes and antinodes. So the first red dot you see on the big graph, it's at a node. You can tell because it doesn't move at all. It sort of stays in the same position, and that's what nodes do. They don't, they're like fixed position. And the second one, you can tell it's an antinode because it moves from one position to the other. And yeah, so yes, these are also the pressure and the displacement time graphs for the graph above, but I'm not gonna get too much into that. Then you also have natural frequency. So every object to some extent has a natural frequency, which is also why soldiers, when they're told to get on the bridge, are told to stop breaking step because they can start marching at the same frequency, such as that the bridge can collapse. This also happens in soap operas, where the voice of the actors uh, or performers goes so high that it can reach the natural frequency of glass and break it. So yes, in essence, every object has a natural frequency, and it's possible to reach it. Uh, Now we're also going to talk about damped oscillations and undamped oscillations. Uh, well, yes, essentially this is a damped oscillation. Everything before what we were talking about was inherently undamped. Um, so a damped oscillation occurs when an oscillating particle experiences resistance. It could be due to like friction or air resistance. And due to this, the amplitude of the oscillation decreases over time, causing the motion to sort of slow down and die out. So we have several lines here to indicate. So the blue one is light dampening. So as you can see, as time goes on, the amplitude of these decreases, which is the distance from the equilibrium to the trough or to the crest. Then we can also see undamped oscillation. So this is the graph what we've been looking at. It starts at one amplitude, continues to minus one amplitude. Then we have heavy damping. Uh, Now they don't show us the waves anymore, but they show us sort of the maximum points of it. And as you can see, it goes down as well. And if you were to draw out the lines, it would also fit perfectly with it. Then you have critical damping, where the damping is so strong that the wave stops oscillating. Well, essentially stops oscillating. Uh, when it reaches like a little less than 6 seconds. But yes, the end. Oh wait, no. The Doppler effect. So, the Doppler effect, as our great teacher Tanala explained to us, uh, can simply be put as a car going wee. So, I think we have a diagram. We have a graph to illustrate that. Uh, which is yes. So, as a source is moving from point A to point B, um, you would observe a lower frequency, and as it's coming to you, you'd observe a higher frequency. This is because the object is in motion. As it's in motion, the wave fronts it's emitting are getting closer. The distance between them is getting closer, so the wavelength is sort of reducing. Uh, well, kind of, yeah. And wait, and yeah. So, and then as it's going away from you, the time it takes for the next wave front to come to you takes more time. So you experience a lower frequency, and then you experience a higher frequency when you're closer to it. So this is why when you have high-speed cars going through, you hear a very first high-pitched sound, and then you hear a very low sound. Next scenario will also help illustrate this. So this is a bat using echolocation. The bat is going through the wall, and it sends out waves of a certain frequency. The wall doesn't move, so the wall is stationary, and then it bounces it back to you. As the object is in motion, it travels a certain distance, one, and then so the frequency it sends out uh is going to be, let's say, like x, right? And since it's moving in that direction, we understand that this value x is going to be compressed wavefronts. So you're going to hear a lower frequency at first. Or yeah, the wall's going to hear a lower frequency. But then as the bat comes closer, there's a distance covered, which is something else, and then the wall is sending it back. But this time, it's the waves are still the same, but it's the observer that's moving. So now we would hear a lower frequency. And so this illustrates. This can also be illustrated using the sun. So if the sun was moving away from us, we'd actually be observing uh, the shadow of the sun, which is sort of highlighted here, because the sun would have covered an amount of distance in that time. But if the sun is moving towards us, it would be the same situation. We'd be moving a shadow of the sun, and the sun would be moving towards us. And this is essentially the Doppler effect. Uh, what you could use in a test is hypercars or supercars theory, which actually is pretty accurate if you don't mess it up like I did. Yes, that should be it, right? Thank you for watching.